So welcome all to week 6 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So this week is going to be last week for linear algebra. From next week, I think we will be starting with calculus, and later on we'll do some parts of probability and statistics. So topics that I plan to cover today is classification metrics. So we'll look at confusion matrix, and then we will look at F1 score, when to use which kind of score, and those kind of things. We will solve some examples of Gram-Schmidt's authorization process, and like depending on the how much time I have left, I'll also try to do polar decomposition, and then Jordan canonical form. My first priority will be Jordan canonical form among these two. So I'll try to solve some examples on Jordan canonical form. At the end, if we have some time left, we'll talk about polar decomposition too. Okay. Okay. So the first thing, okay, so one more thing, if you have any doubt during any time in the session, you can either unmute yourself and speak, or you can type it in the chat box. I'll be happy to help. Okay. So first thing that we're going to cover today is called classification metric. So last time we discussed that in machine learning broadly, you have three kinds of tasks. First is classification, second is regression, and the last one is your reinforcement learning. There can be more tasks, but broadly these are the three domains. Okay. So today we are going to talk about how can we assess the quality of some classification technique. Okay. For example, let's say one of you is using logistic regression. Another one is using, let's say, SVM. Which is better? How do you decide? Okay. So the classification metric give you the quality of your classification model. Okay. Also, one more small thing that you can also have comparison between, let's say, so you train two model, let's say model one, you train logistic regression with some hyperparameter. For example, last time you learned about L2 regularization. There you had a term lambda times W square. So you can train a model with a different value of lambda. Let's say you train with lambda 1 and you train with lambda 2. Then you want to verify or check which one of them is better. So then also you can use this classification metric to check the quality of your model. Okay. So generally, this checking that you do is done on test data set, right? Because the data that you're using to train, there is no meaning of testing it on, like, comparing your models on the same data set, right? So generally, you compare on test data, but based on your need, you can also check on train or validations, train set. So if you have some need, you can evaluate these things on train data set also. So this is indifferent to the kind of data you want to evaluate it on, but you generally do it on test data. Okay. So let's talk about the most common classification metric, that is called as accuracy. Okay. And this is the most intuitive one. Let's say you have 100 data points, right? And you classify 90 of them correctly. Okay. So what is the fraction of points that you have classified correctly? That is 90 by 100, right? So accuracy is just this quantity, whatever we talk right now. It's number of correct prediction divided by total number of prediction that you're making. Okay. So the accuracy over here would be 0.9. Some people write it in terms of percentage, then you will write 90%. Okay. So this is what is accuracy. Okay. This is the most intuitive thing that can come to our mind, right? But there is a drawback of this algorithm. Let's say your data set is imbalanced. Okay. So let me give you an example. So let's say you want to train a model. If you give it image of an animal, okay, it should tell you whether that animal, what is the name of that animal, whether it is a dog or cat, okay. Or let's say, let's consider some rare animal. Sparrows are rare these days. Let's say this, or some more rare animal that is some extinct animal or something like that. Okay. So generally, the data set that you will create, or if you crawl the internet, you will have lots and lots of images of dog, and you will have very few images of the rest of these two classes. Okay. So these kind of data set are called imbalanced data set. Okay. So what are imbalanced data set? Imbalanced data set are those in which you have, so you don't have equal number, equal representation from every class. Okay. So like if you have something like, let's say 100, 101, 105 and 95, this is even a balanced data set. Okay. So like you can't have exactly the same number of data points in every class, but let's say the difference is quite large. Let's say it's 100, then you have some 10 and then 90 and something like that. And this particular class has very low representation in data, right? So this kind of data set are called imbalanced data. Okay. So consider one such setup where you have 1,000 points from class 1 and you have 100 points in class 2. Okay. And let's say you like define a classifier which predicts every point to be of class 1. Okay. So no matter what input you give, it predicts everything to be class 1. Okay. So you can clearly say that it is a very poor classifier, right? Because it gives you like no information about class 2. So it is a very poor classifier, right? But if you calculate its accuracy is number of correct prediction divided by total number of prediction. So if you are predicting everything to be class 1, then you are making 1,000 correct predictions. So accuracy is 1,000 divided by 1,000 plus 100, right? This is the total number of prediction that you are making. So this is 1,000 divided by 1,100, which is something like 10 by 11, and this fraction is approximately equal to 0.9. So you're achieving 90% accuracy by just doing almost nothing, right? You are just predicting everything to be of class 1. You are doing nothing. It's a very poor classifier, but you are getting 90% accuracy. Okay. So to deal with this kind of setup, we define special metric for imbalanced data set, right? So one such metric is confusion metric. Okay. So I will just clarify. This is more mathematical. So if you look at the term metric, metric, metric means distance. Okay. In mathematics, metric means distance. Okay. And matrix is what you have been doing. So the pronunciation is quite similar, but they are two different words. So matrix is a two-dimensional representation of data, and metric is distance, or you can say, like in the context that we are using, refers to quality. Okay. So accuracy gives you the quality of your classification model. Okay, so one such classification metric is this confusion matrix. Okay, so this is for data set having two classes. Okay, let's say you have two classes. Then let's say this is classes are called positive class and negative class. Okay, then when you classify elements of positive class, either they can be classified as positive or they can be classified as negative. Similarly, a negative class data point can be predicted as positive or they can be predicted as negative. Right. Now, whatever information we have in this small diagram that I have drawn over here, we write it in terms of a matrix. Okay. On the top, you have actual label, and every row is corresponding to predicted label. Okay. So what I mean by this, so if you look at the first row correspond to your predicted label is positive. Okay. So here what we had, so if you look at these kind of things, so this positive and this positive, so your prediction that you're making is positive, right? This corresponds to your first row. Okay. And first column corresponds that actually that data point was positive. Okay. So if you look at the intersection of these two things, so first element of this matrix would mean what are the points which were actually positive and were also classified as positive. So they are talking about these points. So the points that were actually positive and were also classified to be positive. And these are called true positives. Okay. Similarly, what does false positive means? So one row corresponds to predicted label. So this means it was predicted positive, but it's actually negative. Okay, so this is false positive. So this was false positive is predicted positive, actually negative. So we are talking about this particular branch. So it was actually negative, but was predicted positive. This is false negative. Similarly, you have false negative. So false negative are which are actually negative but predicted, sorry, which are actually positive but predicted negative. So they have been falsely classified as negative. And true negative are which are actually negative and also predicted to be negative. Okay. So if you write these four numbers in terms of a matrix, this matrix is called confusion matrix. Okay. Let's have a look at an example. Here is an example. So we are given with actual label, whether it is a dog or not dog. Okay. And we are also given with predicted label. So because it was a dog and it is predicted as dog, so this comes as true positive element. Okay. Similarly, it was a dog but predicted as not dog. So it has been falsely classified as negative. So it is false negative. Okay. Let's look at this example. It is not a dog and it is also classified as not dog. So it is true negative. That it is negative and classified also as negative. Okay. And yeah, this example. Actual level is that it is not a dog, but classified as a dog. So it has been falsely classified as a dog. So this is a false positive. Okay. So now if we want to create the confusion matrix out of this table that we have given, the first element will be total number of true positives. How many true positives are there? 1, 2, 3. Okay, let me use this. There is 1, 2, 3, 4, 5. Right. So there are 5 true positives. Then I want to look at false positive. Okay. So there is 1. I think there is only one false positive. Right. So this is 1. Then this is false negative. This is 1. Yeah, I think it's only 1. right? And then I have 3 true negative, right? So this matrix now gives you a matrix, but yeah, like it gives you an idea how your classification model is performing. So if your classification model performs well, then your entries on diagonal should be high and your entries on off diagonal should be low. So your entries over here should be low and entries on the diagonal should be high. Okay. These value, you want them to be low and you want these value to be high, right? Okay. So right now we just took an example where we had two class. Okay. Before I move forward, any doubt in whatever we have discussed, you can ask if you have any doubt, something is not clear. So that when we go ahead, you don't have doubts from previous section. Okay, if you have no doubt, we can proceed further. Okay, now the question is, what about when you have multi-class classification? You have more than two classes. Okay, so there are two options. Rather than saying that we have two options, I'll rephrase it. Okay, so what you do is, for every class, you treat that class as positive class and treat everything else as negative class. And this is how you will sort of create the matrix. I'll give you an example. Okay. So we can come to this example slightly. I think I should have more examples. No, I don't have. Okay, let me see if I have some example of multiple classes. Mm. Okay, I have an example. I'll get to that example in a while. So let me explain what I mean, like what about what needs to be done. So let's say you have three classes. Let's say this is cat, this is dog, and let's say this is rat. Okay, cat, dog, and rat. So what would this entry correspond to is, this is number of data points which were actually cat and was also classified as cat. Okay, this is what this entry would mean. Okay, I'll give you one more random entry. Let's say this entry. This entry means that the data point that you have is actually dog, but it has been wrongly classified as rat. Okay, this is how you will create the confusion matrix for your multi-class setup. Okay, so you will fill in these entries and you will get your confusion matrix. Okay, now one very interesting thing that you all must have observed, and like let's say I tell you to compare two numbers. Let's say I have 5. So okay, so somebody has got, let's say, 95 marks out of 100. Somebody has got, let's say, 82 marks out of 100. Okay, so who do you think has performed better? Clearly, when you have real numbers, you can compare these two numbers, right? And you can say which one of them is better, right? So real number has a property that is called as totally ordered set. So if you someday do a course on discrete mathematics, you will know what is totally ordered set, and real number is even actually a totally ordered set. Okay. But let's say somebody asks you to compare two vectors. Let's say one of them is 1, 0, another one is 0, 1, right? So how do you compare these two vectors, right? There is no straight way to compare these vectors. No straight away to compare vectors, right? And same is true for your matrix too, right? For example, if you have matrix 1, 0, 0, 2 and 2, 0, 0, 1 problem, how do you compare these two matrices? So whatever confusion matrix that you have obtained now are matrix, right? So if you have two models, you will get confusion matrix 1 and confusion matrix 2. So this corresponding to model 1, this corresponding to model 2. How do you compare these two matrices to infer which is better and which is bad? This is not possible, right? So that's why we need some reduction to these matrices. Okay. So let's get back to the marks example that I gave you. Now let's say every students appear in exam for two subjects. Let's say in machine learning, first student scores 50 out of 100, and in math, probably let's say linear algebra, he scored 60 out of 100. Okay, and the second student, let's say he scores 55 in machine learning, and let's say 51 in linear algebra. Then if somebody asks you who performs better, what you would do, like most intuitive thing that you can do is you can take the average of these two entries, right? So average would be 55. Here you will have, so there's a difference of 4. So you will have 53 as your average. So then you can infer that the first person has performed better than the second person, right? So what we have done is we have reduced our vector to a single number, and then we have compared them. Okay, so this is the idea behind this definitions that I'm doing. So we will solve this question after I have defined these things. Okay, so first thing that we can derive out of confusion matrix is accuracy. Okay, this accuracy is exactly same as the accuracy that we discussed initially during our lecture. So this is number of correct prediction divided by total number of prediction. Okay. So you can clearly say if you add true positive, true negative, and false negative, this is an exhaustive set. So you have included everything. So your denominator is nothing but total number of prediction that you have made, right? Because you have included everything and you have added them in the matrix, this is total number of prediction that you have. So let me draw the matrix again. This is true positive. This was false positive. This was false negative. This was true negative. Okay. And what is the correct number of like number of correct prediction that you have made? That is this true positive and true negative. So you add them on top, true positive, true negative, right? This is how you obtain your accuracy. Okay. But we wanted to move away from accuracy so that we can give some good metric for imbalanced data set. But we have landed back to accuracy. So we will define some more matrices which are more useful for the imbalanced data set. First one of them is precision. Okay. Precision is, like, I'll state it in simple English. So if you look at the denominator, this is true positive plus false positive. That is, this is sum of this row, right? So out of all points that you have predicted to be positive, what is the fraction of data points which are actually positive? This is what precision gives you. So this is true positive divided by true positive plus false positive. So out of all points that you have predicted to be positive, what is the fraction of points which are actually positive? This is your precision. Okay. Then you have one more thing, that is recall. Recall is true positive divided by true positive plus false negative. Now, what is true positive plus false negative? It is this column. Okay. So denominator is total number of points which were actually positive. Points which were actually positive. So out of total positive points, how many of them were you able to recover? That is given by recall. Okay. So now these two are some special matrices which are very useful for your imbalanced data set. Okay. So you have derived these values from your confusion matrix, right? But still you have two values, right? To compare two models, you need only one value. So we now combine both these two things, precision and recall, using something called as F1 score. F1 score is given by 2 times precision into recall divided by precision plus recall. Okay. And this is the score that we are gonna compare. Okay. So this is F1 score. So like if you look at two most common classification metric being used these days, first one is accuracy. If you know that your data set is balanced, then you should go for accuracy. And the second one is F1 score. If you know that your data set is imbalanced, then you should go for F1 score. Okay. Okay. Let's look at this example that I had. So the example says 165 patients were tested for the presence of a disease. Predicting the presence of a disease using binary classifier, we obtain the following confusion matrix. Okay. What is the total number of actual positive samples? Okay, so you guys tell me what is the total number of I'll wait for 2 minutes. You guys just solve and comment what is the correct answer for this. Okay, somebody said, can you please again say about imbalance? Okay, Dr. Victor, what does imbalance data mean is, let's say you have two classes in your data set. Let's say one is image of dog, right? Another one is, let's say, image of cat. Okay. So let's say you have 1,000 images of dogs, right? And you have only 10 images of cat. So such data sets are called imbalanced data set. When you have more number of data points belonging to a certain class and much lesser number of data points belonging to other class, that kind of setup is called imbalanced data set. Okay. So I gave a motivation that if you calculate accuracy in such cases, accuracy can be very misleading. For example, let's say you classify every point that you encounter as image of a dog. Okay. Then your accuracy would be something like 1000 divided by 1010, which is a very high number. Okay. Very close to 1. So to elope from this kind of situation, we defined this F1 score. Okay. So what I said was, if you have a data set that you know is balanced, then you should calculate accuracy. If you know a data set which is imbalanced, then you should go for calculating F1 score. Okay. Okay. Now, can you guys please attempt this question and tell me what is the total number of actual positive samples? So you are given with this true positive, false negative, false positive, and true negative. You have to just tell me what is total number of actual positive samples. Somebody says 100. Okay. Other also, please, can you please try so that I can confirm whether two of you are getting same answer or all of you are getting.
Is it 105?
Somebody says 105, somebody says 100. Okay. Okay. So total number of actual positive samples, okay, is true positive. So data points that were actually positive and classified as positive plus false negative. Okay. Data points which are positive but classified as false or classified as negative. Okay. So it would be 90 plus 15. Okay, which would be 105. So the way in which we wrote our matrix, we had predicted values row wise, right? And we had actual values column wise. Here they have just reversed that thing. So I included this example to tell you that people can use different kind of notation, but you just stick to one of them and you should be fine with it. Okay. So the correct answer is 105. Okay. Now let's go on to calculating these values. So you have a confusion matrix given over here. You have true positive, false, false negative, and then you have true negative. This is similar to what we have discussed, right? The formatting over here is similar to what we have discussed. And we have been asked to calculate precision, recall, and F1 score. Okay, so let me calculate for you. So precision is given by true positive divided by true positive plus false negative, false positive, sorry, which is true positive is 560 divided by 560 plus 50. So this is 56 by 61. So I'm not going for the exact value, but this is what we get. Okay. Similarly, you can calculate the recall. Recall again is true positive divided by true positive plus false negative, which is given by 560 divided by false. Okay, I think I made a mistake. This should have been false positive, right? Yeah, this is false positive that I have written here. But the value that I have written is for false negative. This should have been 60 here, right? So you will get 56 by 62. And here you will get that 560 plus 50, that is 56 by 61. Okay. Then you can put it in the formula of F1 score to calculate your F1 score. Okay. Any doubt in calculating precision recall and those kind of things before I move ahead to talk about how do we do these things for multi-class setup? Any doubt if you have, you can ask. Okay. So again, the question is, what should we do for multi-class setup? Okay. So you can calculate precision for a class, right? You can calculate accuracy, sorry, recall for a class. And hence you can calculate F1 score for a class. But now you have multiple classes. Again, you run into the same problem that you have vector value. So you will have F1 score corresponding to class 1. Then you have F1 score corresponding to class 2 and F1 score corresponding to class 3. How do you merge them to get single value? Okay. So there are three ways to do that. First, the most common ones are macro F1 score. Okay. Second is called micro F1 score. And the last one is called weighted F1 score. Okay. So we'll talk about all three of them. Okay. So first of all, let's talk about macro F1 score. So in macro F1 score, you calculate the F1 score of all the classes, and then you just take the average of the F1 scores. Okay. So let me just take an example. So this example I have taken from this website. Okay. So let's say there are three classes. This is airplane, boat, and car. Now again, this is reverse to what we assume. So we have one row corresponding to actual label now and a column corresponding to predicted label. Okay. So we have three classes and these values have been calculated. Okay. So you have aeroplane being predicted as aeroplane to be 2, aeroplane being predicted to boat. No, okay. So a boat being predicted, no, aeroplane being predicted to boat is 1. So this entry is aeroplane being predicted as boat. Okay. So let's look at how can you create the confusion matrix for this. So this is the confusion matrix for your data that is given over here. So let's look at it one by one. So for aeroplane, what is a true positive? True positive are points which are actually positive and are also predicted to be positive. Okay. So what is true positive here? So the number of points which are aeroplane and also predicted to be aeroplane is 2, right? So you can calculate this true negative also over here. You might be wondering why we have only 3 entries over here. But because we are interested in calculating F1 score, you can see that in F1 score, we don't use true negative anywhere. Okay. So that's why we are not explicitly calculating it, but you can calculate it for every class. Okay. Now, second entry over here is false positive. So points which are not positive, but predicted positive. But predicted positive. Okay. So what are the points which are not aeroplane, but predicted as aeroplane? So there is only one point over here. So it has been predicted as aeroplane, but it's actually car. Okay. So there is only one point in false positive. False negative is points which are aeroplane, but are not predicted to be aeroplane. They are predicted to be something else. So if you look at this row, so there is this point. So this is aeroplane, but predicted as boat. So there is one false negative also. Okay. Similarly, boat being predicted as boat 1, which are predicted as boat but not boat, are these two entries. First one is this, second one is this. So 1 plus 2 is 3, right? Then which are boat but predicted as something else. 0 plus 0, 0. Okay. Car, from here you have 3. False positive, from here you have 0. And you have some of these two as 3 as your false entry. Okay. So now for every class, you have true positive, you have false positive and false negative. So you can calculate its precision and recall. So let's say for the first class, you want to calculate its precision. Precision is given by 2 divided by 2 plus false positive, right? So this is 2 by 3, this is 0.67. Okay. What is recall? Recall is 2 divided by 2 plus 1 is again 0.67. Okay. What is your precision for the second one? Precision is true positive 1 divided by 1 plus false positive. So 1 plus 3, this is 0.25. So it is doing pretty well, pretty bad on this particular class. Okay. And the last one is your recall. This is 1 divided by 1 plus 0 is 1. Okay. And what is for the third one? Precision is 3 divided by 3 plus 0 is 1. And what is recall? Recall is 3 plus 3 is 0.5. Okay. And this is what they have calculated. They have calculated precision, then they have calculated recall for every class, and it matches with whatever we have calculated, right? Then we go to calculating the F1 score. F1 score is 2 times precision into recall divided by precision plus recall. So for the first one, it is 2 into 0.67 divided by 0.67 plus 0.67. Right, this is clearly, so this is, yeah. Okay, so this is one more 0.67 is missing here, because this is 2 times precision into recall, right? So this 0.67 plus 0.67 is 2 times 0.67. So this and this gets cancelled. So we are left with 0.67. For the second entry, we have 2 times precision is your 0.25. Recall is 1 divided by 1.25, right? So what we can do is, what is 1.25 is 5 by 4, right? So this is something like 2 into 1 by 4 into 1 divided by 5 by 4. This is something like 2 by 5, which is 0.4. Okay, so this is what we have obtained. And similarly over here. So for all 3 classes, you have obtained one value for F1 score. Now you want to somehow merge them so that you get a single value. Now, as I said, what is macro F1 score? Macro F1 score is just average of F1 score. Okay, so this is 0.67 plus 0.67, sorry, 0.4 plus 0.67 divided by 3. This is your macro F1 score. So you just take average value of all the F1 score and you obtain your macro F1 score. Okay. So there is something called as weighted F1 score. Let's say in your application, uh, predicting whether your class is aeroplane or not carries most importance. So what you can do is, you can give some high weightage to your airplane F1 score. So what you do is, you just take something like W1 times F1 score of class 1 plus W2 times F1 score of class 2 plus W3 times F1 score of class 3, right? And your W1 comma W2, W3, all these are values between 0 to 1, and W1 plus W2 plus W3 should be equal to 1, right? So you can take weighted average like, let's say you want to give 0.6 weightage to F1C1, you want to give 0.2 weightage to F1C2, and then again 0.2 weightage to F1C3, right? So this is an example of weighted average score. Okay. 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 So now we have something that is called as micro F1 score. So in calculating micro F1 score, you calculate the overall precision and recall of your data set. What do I mean by overall precision and recall? If I just copy this table. Okay. So how do you go about micro F1 score is, so let's say you have this kind of data set, or you have this kind of confusion matrix that you have obtained. Then what you do is, you calculate the total number of true positives. So what is the total number of true positive? 336, right? What is total number of false positive across classes? So this is 4, this is also 4, right? So then its precision is given by total number of true positives, that is 6, divided by total number of true positives plus total number of false positives. So this is 0.6. And again, your recall is 6 divided by 6 plus 4 is again 0.6. And your micro F1 score is, now you calculate your micro F1 score based on this precision and recall. This is 2 times 0.6 into 0.6 divided by 0.6 plus 0.6, which is again 0.6. Okay. So this is how you calculate micro F1 score, macro F1 score, and weighted average score. Okay. So all this story began from a point where we wanted to define a suitable metric for imbalanced data set. We have come up different F1 scores, macro, micro, and weighted. Which one should you use? Okay. So for imbalanced data set, you should prefer macro F1 score. So if you have imbalanced data set, you should calculate your macro F1 score. If you know your data set is balanced, then go for micro. Now, the third case is when you want to give some more weight to some particular class. Okay. Then you will go for weighted F1 score. Okay. Okay. Any doubt till this point? This was the story so far about F classification metric. Now we will go to Graham-Smith's process and those kind of things. But before that, if you have any doubt.
Hello, sir.
Hello.
Yes, sir. Sir, in examination, whether they mention to TP true positive or false positive like that in the questions.
Like if they will ask you to calculate F1 square, they should mention. But if they don't mention, you will probably get something like this. I'll give it. So if you look at this example, they might also give you something like this, where they'll just give you the top two rows. They will just a second. They might not give you this last one, but you will have to yourself check whether it is a true positive point or false positive point. But this much information must be given to you doing for some.
Okay, sir. Suppose if we have two cross two matrices like two rows and two columns,
Mhm.
first row named as positive, second row is negative.
Okay, so that depends on convention that we just saw. For example, the way I discussed, I wrote first entry as true positive, right? Then I wrote
Okay, sir.
false positive. But there were example where they sort of wrote other way around. So it depends on convention whether you are writing whether a row corresponds to actual prediction, actual labels or predicted labels. It will depend on that.
Okay, sir. I understood, sir. I understood. Okay, sir. Thank you, sir. We
Okay.
understood, sir.
Okay, so as we are now changing the topic and we are almost discussing these things for an hour, we can take a 2-3 minutes break uh, rather than sitting in a stress for 2 hours. It's better to take a break. So I'll start again at 6:56. Okay, I'll take a 2-3 minutes break. We can meet again at 6:56. Then we will probably discuss about Graham-Smith's authorialization process, and probably later we'll do Jordan canonical form. Okay, I'll start again. Okay. So this Gram-Schmidt's process, uh, okay, is used to, so if you are given a set of basis vector and you want to convert it to set of orthogonal basis vector, then you use this Gram-Schmidt's optimization process. Okay. So just a reminder, what is meant by orthogonal vectors? So two vectors v1 and v2 are orthogonal if the inner product between them is 0. And what are orthonormal vectors? So this is orthogonal. Apart from it, if you have this condition that norm of v1 and norm of v2 both are equal to 1, then together these conditions are called orthonormal vectors. Okay. So you can convert your any given set of basis vectors into an orthogonal basis and further into an orthonormal basis. Okay. So why is it useful is, let's say if you have an orthonormal basis or an orthogonal basis, then what you do, let's say I give you a random basis, let's say 1, 2, 3 and 0, 1, 0, 4, 7. Okay. This is, okay, I need one more element. This is, let's say 1, 4, 0. Okay. This is a valid basis for R3, right? You can write any element in R3 in a linear combination of these three vectors. Okay. But if I give you a random vector, let's say 5, 0, 5, and ask you to write this vector in terms of basis element, like a linear combination of these three basis elements, then you will have to solve a system of linear equation to get to an answer, right? So this is not straightforward. But if you have an orthogonal basis, you can straight away get the coordinates. Okay, so what is the coordinate? So if you have any arbitrary vector y that you want to write in terms of v1, v2, vk, so let's say v1, v2, okay, let me read out the theorem. So let v be an inner product space. So you just assume that v is a vector space and you have defined some inner product on top of it. So if you have a vector space over which you have defined an inner product, that space is called inner product space. Okay. And this is your orthogonal basis. Okay. Then what you can do is, if you have any arbitrary y, you want to write it as linear combination of v1, v2, vn. So what you will do is you will have some vi. This is how you write as linear combination, right? Then your bi's are given by nothing but you take dot product of y with bi divided by norm of bi. This is for orthogonal. If you have orthonormal, you can ignore this norm also. So if you have y, if you have bi, you can straight away get these bi's that were difficult to solve in case of any arbitrary setup. Okay. So this is how it makes our life easier if you have an orthogonal basis. Okay. And if you look at what does this term signify, this bi, this is projection of y onto your vector vi. Okay. So if you have, let's say this is vector a, this is some vector b, right? And if you take projection of a onto b, it is given by this particular a dot b divided by norm of b. So this is nothing but projection of y onto bi. Okay. So I can give you one more example over here. Just to solidify things, let's say you have a two-dimension. So this is x-axis, this is y-axis, right? If you write a vector, let's say this is probably 2 comma 1.5. Let's say this is my vector. So when you write 2 comma 1.5, what does this mean? Okay, this actually means is this is 2 times 1 0 plus 1.5 times 0 1, right? This is what it means, right? Now, how have you calculated this 2 and 1? If you recall, this is nothing but the x-axis. So how do you obtain this x-axis? You take projection of this vector onto your x-axis. Whatever value you have, that is your v1, right? Similarly for y-axis, you take its projection, whatever value you have, that is your v. And something similar happens if you have an orthogonal basis, right? So you can just take the projection, and that is your coordinate corresponding to that particular choice of basis. It is very similar to what you do in R2 coordinate or Rn coordinate. When you take x, y, z, these kind of things as your basis vector. You can clearly see that your x and y are orthonormal or orthogonal basis elements. Okay. So the standard basis that you have, E1, E2, En, these are your orthonormal bases. Orthonormal basis. Okay. Okay. So now this is a theorem that is given. More than theorem, this is an algorithm how you can convert your any given vector into this orthogonal basis. But I'll just solve an example to help you understand how you can do it. Okay. So this process is pretty simple. So let's say you are given with three vectors you are given over here, W1, W2, W3. So in step one, okay, so your goal is you want to construct V1, V2, V3, which are orthogonal. So first I'll solve for orthogonal and then I'll tell you how to convert to orthonormal. Okay. So your goal is you want to find V1, V2, V3, which are orthogonal in nature. Okay. So step one would be assign V1 is equal to W1. Okay. So V1 become now V1 becomes 1 0 1 0. Okay. Step two is when you find V2, V2 is given by W2 minus W2 dot product with V1 norm of V1 times V1. So what I'm doing is I'm taking the projection of W2 in direction of V1 and subtracting it from there. Okay. So whatever I get in direction of V1, whatever component is there in direction of V1, I'm subtracting that from W2. Okay. This is how I will obtain V2. Okay. So let's solve this. So my V2 is given as 1 1 1 1. So this is 1 1 1 1, right? Let's take the dot product W2 and V1. So this is my V1. W2 is here. So this is 1 times 1 is 1 plus 0 plus 1 plus 0. This is 2, right? What is norm of V1? This is square root of 1 plus 0 plus 1 plus 0. This is square root of 2 V1. Okay. So what do we obtain? We obtain 1 1 1 1 minus root 2 times V1. So root 2 0 root 2 0. Okay. And this is what we have obtained. This is 1 minus root 2. Zero. Sorry, this is 1. Then this is again 1 minus root 2. Okay. This is what I have obtained my V2 to be. Okay. I hope this is correct. Okay, sorry, this is norm square, not norm. So I will have 2 only over here. Okay, so this is norm square. So this we obtain as minus 1, 1, minus 1, 1. Okay. Okay, so just a second. I think, right. Yeah, I have made a mistake, and it's a very elementary mistake, because if you see, what we wanted is that V1 and V2 should be orthogonal, right? And if you look at these matrix, this and this matrix, these are not orthogonal, right? So the mistake that I have made is, so this is norm square, so the denominator becomes 2 divided by 2, right? And this becomes minus 1 times this. This is 1, 0, 1, 0, and you obtain 0, 1, 0, 1. Okay, I'll repeat whatever I have done because there was some confusion here. Okay, so what you do is you assign your V1 as W1, okay, and then what you do is for your V2, you subtract the projection of W2 in the direction of V1 from W2. So W2 minus W2 inner product with W1 divided by W1 norm. Here is where I had made the mistake. I didn't took the square of this norm. So this is norm square times V1. Okay. So if you look at it carefully, W2 is 1, 1, 1, 1. Dot product is 2. Norm square is 2. V1. So this is 1 times V1. So we obtain our V2. Okay. Now, when you go for V3, you will have to subtract both these terms, one corresponding to V2, one corresponding to V3, sorry, V1. So what you do is you do W3 minus W3's projection along the direction of V1. Right, this is a common term between V2 and V3, right? And then okay, and this is the way you will keep proceeding. So here we had only 3 vectors. If we had more vectors, we would have subtracted more vectors in future. Okay, so let's solve this. So W3 is given by 0, 1, 2, 1. So this is 0, 1, 2, 1 minus this is again W3 dot product with, so this is W3 is your 0, 1, 2, 1. V1 is given by 1, 0, 1, 0. V2 is given by 0, 1, 0, 1. So if you take dot product between W3 and V1, you get 0, 0, and 2. So this is minus 2. Norm is again 2 times 1, 0, 1, 0. Then you take its dot product with the V2. This is 0, 1, 0, 1. 1 plus 1 is 2. Norm is again 2. And you have 0, 1, 0, 1. So what you obtain is, so your first entry is 0 minus 1 minus 0 minus 1. 1 minus 0 minus 1, 0. 2 minus 1 minus 0, 1. And the last entry is 1 minus 0 minus 1, 0. So this is what you obtain. So you can clearly check if you take its dot product with this entry, V1 you will get minus 1 plus 1 is 0. And if you take its dot product with the V2, then also you will get 0. So this is the set that you have obtained. So set of orthonormal bases that you have obtained is your V1 is equal to 1 0 1 0, V2 is equal to 0 1 0 1, and V3 is equal to minus 1 0 1 0. Okay. Now if somebody asks you to find orthonormal basis, you just normalize V1 and V2 and V3. So your O1 would be given by V1 by norm V1. Okay. So this is 1 by root 2, 0, 1 by root 2, 0. Then V2 is again given by 0, 1 by root 2, 0, 1 by root 2. This is your O2. And O3 is given by again minus 1 by root 2, 0, 1 by root 2, 0. Okay. This is how you can reach an orthonormal basis. Any doubt in Gram-Schmidt's process? You can ask now. Okay. So I'll move ahead. Okay. So before coming back to this polar decomposition, first of all, we will do Jordan canonical form. Okay, that is more useful. So all of us have already discussed about eigen decomposition. Okay, first I'll motivate why do we do these kind of things. Okay. We already did eigen decomposition, right? What we did in eigen decomposition is, for some matrix A, we want to write it in form P, let's say D, P inverse, okay, where P contains all your eigenvectors, D is a diagonal matrix, and P inverse is P inverse, right? So one application that I discussed at that time is, let's say if you want to calculate A to the power n, then it is nothing but P D to the power n, P inverse, right? Where D is your diagonal matrix, so taking D to the power n is very easy. For example, let's say your matrix is something like this 1 0 0 2. This to the power 100 is nothing but 1 to the power 100, right? 0 0 2 to the power 100. So calculating power of matrix becomes very easy when you have eigen decomposition of a matrix. Okay. But we also discussed that eigen decomposition of every matrix is not possible. Okay. So what we want to do is, we want to find something that is known as Jordan decomposition. Okay. And that is given by your, so this eigen decomposition was not possible for every matrix, every square matrix, but your Jordan decomposition is always possible, always exists for any arbitrary square matrix. Okay. So your A is given by some PJP inverse, where J is a Jordan block matrix. We'll talk about what is Jordan block matrix. And it is not as easy as like raising diagonal matrix to the power n, but it has some special rule by which you can manipulate J to the power n and those kind of things. Okay. So this is also pretty much useful. It is not a waste. Okay. So this is the motivation. Okay. And yeah. Okay. So first of all, the first thing that I want to say is, what is a minimum polynomial of a matrix? So the definition goes something like unique minimum degree monic polynomial such that m lambda of A is equal to 0. Okay. So it's a minimum degree polynomial, okay, of one variable. Monic polynomial means one variable polynomial. So that if, let's say, your polynomial is given by lambda square plus 1 minus, okay, lambda square plus 1 minus 2 is, right? This is your polynomial. If you replace your lambda by A, you should obtain 0. Okay. So it is the minimum degree polynomial so that you can do something like that. That is called the minimum polynomial of your matrix. Okay. So this I think we discussed when we discussed eigenvalue and eigenvector. Okay. Now let's say A is your matrix. Okay. And B is also your matrix. You create a block diagonal matrix. So what is this matrix? Let's say A is your 1, 2, 3, 4. B is your 1, 2, 1, 1. Then this A plus B, it's written in short form over here, but it is something like 1, 2, 3, 4, then 2 zeros. This is a zero matrix. And then you have 1, 2, 1, 1. This is what you mean by A, this sum, special kind of sum B. Okay. And if you join your matrix in this form, then the characteristic polynomial of this joint matrix is the product of characteristic polynomial of A and B. But the minimal polynomial is LCM of both the minimum polynomials. Okay, the minimal polynomial of A and the minimal polynomial of B. It is LCM of both of them. I'll take an example. Let's say A has characteristic polynomial as lambda minus 2 square, and B has, let's say, lambda minus 2 to the power 4, right? Then characteristic polynomial would be multiplication of both, that is lambda minus 2 to the power 6, right? But the minimal polynomial would be the LCM. Okay, so let me just take the space. So LCM of lambda minus 2 whole square and lambda minus 2 to the power 4 would be given by lambda minus 2 to the power 4, right? Okay. This was discussed in the lecture, so I discussed. Now I'll get to the what is known as Jordan canonical form. Okay, so this is what I already discussed, that why do we want something like this? So this is J S J inverse. We want something like this, where J is a Jordan block matrix. And now because you don't have enough number of eigenvectors, this S matrix, so for example, in eigen decomposition, you had PDP inverse. This P consisted of your eigenvectors, right? But because now you don't have enough number of eigenvectors, what you will do is you will go for something that is known as generalized eigenvectors. Okay, I'll discuss what is generalized eigenvector and all those kind of things. Okay, we'll do full-fledged example on this. Don't worry about it. Right now, I'm just explaining you the terminologies. Okay, there is something that is known as arithmetic mean. It is the number of times an eigenvalue is repeated. Okay, so when you calculate the eigenvalue, you repeat some eigenvalue sometimes. Okay, so the number of times a particular eigenvalue is repeated is called the uh, arithmetic mean, and geometric mean is the number of linearly independent eigenvector that you have corresponding to an eigenvalue. That is called geometric mean. Okay. Okay. Now this was all discussion. Now we'll get something serious and see what we have to solve. Okay. First important thing in finding out Jordan canonical form is Jordan block. Okay. So if what is Jordan block is not clear to you, I request you to please stop me and interrupt me there. Okay. So Jordan block, so this J n lambda means Jordan block of size n for eigenvalue lambda. This is what this notation means. Jordan block of size n for eigenvalue lambda. Okay. This is an n cross n matrix, right? So how does this matrix look? You will have lambda on your diagonal as your diagonal entry. You will have 1 on your super diagonal entry. Okay. And you will have 0 elsewhere. Okay. This is how you give Jordan block. I'll take 1 or 2 examples. For example, if somebody asks you to write Jordan block of size 2 for eigenvalue, let's say 2, that matrix would look like 2, 2, 1 on the off diagonal, and everything rest is 0. Okay. Let's say somebody gives you Z3 of 1, right? This would look like 1 on the diagonal, then 1 on the super diagonal, 0 elsewhere. Okay. This is how your Jordan blocks look like. Okay. I'll come to generalized eigenvectors later on. Okay, let's first look at what is Jordan canonical form. Okay, I'll come to generalized eigenvector for sure. Okay, so let's say for some matrix, your characteristic polynomial looks something like this: lambda minus 2 square, right, multiplied by lambda minus 3. Okay, it looks something like this. So because your 3 is repeated only once, you will surely have one independent eigenvector. That is for sure. If your geometric mean or arithmetic mean is 1, like here you will have arithmetic mean to be 1, then you surely have one independent vector. This we have done, right? And let's say in some case you only had one Li vector over here also. Okay. Now, in order to write an eigen decomposition, what you would have expected is that you get two linearly independent eigenvectors. Okay. But if you get only one linearly independent eigenvector, then you create something that is known as Jordan canonical, right? How you create it, I'll tell you. Okay. So in order to create Jordan canonical form, you remember these two rules. Okay. Your geometric mean tells you the number of Jordan. No, okay. Let me modify this in a way that is more easier to understand. Okay. Arithmetic means give you sum of size of Jordan block. Okay. And this gives you the number of Jordan blocks. Okay. So if you look at this example, because you have one linearly independent eigenvector, for lambda is equal to 2, your geometric mean is 1 and your arithmetic mean is 2. So arithmetic mean gives you the sum of size of Jordan block, and geometric mean gives you the number of Jordan block, right? So you will have one Jordan block of size 2. Here your AM and GM both are 1, so you will have one one Jordan block of size 1. Okay. So how does your Jordan block looks like? Jordan canonical form looks like. Let's look at that. So what it said is you will have one Jordan block of size 2. So how did we define Jordan block of size 2? With eigenvector z2, sorry, eigenvalue 2. This is 2, 2, 1, 0. So you will have 2, 2, 1, 0. Okay. This is one block. And then you will have one block with 3, right? One block of size this. So we can rub most part of it because this is not that fat matrix. Okay. And rest everything will be filled by 0. Okay. So this is the Jordan canonical form. Of this particular example that we had. Okay. Let's look at one more example. I think then things will be much more clear to you. So let's look at this example. So you are given with a matrix A. We want to find its Jordan canonical form. Okay. So I'll go step by step. First of all, let's find its eigenvalues. Okay. Now I have taken a simple example because this is an upper triangular matrix. So its eigenvalues are elements on its diagonal. If you don't know this property, then you just remember this. If you have an upper diagonal matrix, then its eigenvalues will be elements on the diagonal. So lambda is equal to 1, 1, 1. What does this mean? Its arithmetic multiplicity is 3. That is, it is repeated 3 times, right? This is 1 minus lambda to the power 3. This is its characteristic polynomial, right? Okay. Now, we want to find its geometric multiplicity, or we want to solve a minus lambda I, b is equal to 0. Okay. So let's solve it. So this is given by this a minus lambda is 0, 1, 1, 0, 0, 0, 0, 0, 0. V1, V2, V3. Okay. So what does this give? This gives that V2 plus V3, okay, this is 0. V2 plus V3 is 0, or V2 is equal to minus of V3, and your V1 is independent, free. If you choose your V2, your V3 gets chosen, right? So what are the linearly independent eigenvectors you can get based on this condition? These are, so 1 is free, one time let's choose it to be 0, then 1 and minus 1, and second one is 1, 1 and minus 1, right? These are your two linearly independent eigenvectors. So its geometric multiplicity is 2. Okay. So if you wanted an eigen decomposition, you should have obtained 3 linearly independent vectors. But you have obtained only 2 linearly independent eigenvectors. Okay. So you have to find its Jordan canonical form. Okay. Now geometric mean gives you number of Jordan blocks. So you have 2 Jordan blocks, and total sum of size of Jordan blocks is 3, right? So it can be either of form 1 plus 2, or it can be of form 2 plus 1. So there are 2 possible Jordan canonical forms for this one. If you go for 1 plus 2, you will have 1. This is your 1 cross 1. Then you will have 1, 1, 1, 0, and 0 elsewhere. Another option is, if you go for 2 first, and then 1, you have 0, 0, right? These are the 2 possible Jordan canonical form. Okay. So when I motivated this, I told you that we want something of this form, SJS inverse. Okay. This whatever we have obtained is just the J part of it. Okay. Now how do we obtain S? We will come to this. Okay. So this is something that is known as generalized eigenvector. Okay. So when you had eigen decomposition, let's say A is equal to PDP inverse. Okay. Then your P consisted of these columns were eigenvectors of A. Okay. Now if you have Jordan canonical form, then your S has eigenvectors plus generalized eigenvectors of A. Okay. So let's take this example, whatever we did. For this example, for lambda is equal to 1, we have 2 Li eigenvector, right? But we wanted to solve, so in order to find its decomposition, we wanted 3 vectors. Okay. So we will find one generalized eigenvector. Okay. 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 So how is generalized eigenvector defined? It's so how was eigenvector defined? Eigenvector is a non-zero vector V satisfying this, right? This is what was our eigenvector. Now what is generalized eigenvector? Generalized eigenvector is an vector V, non-zero vector V, satisfying this such that, okay. So rather than just power 1, we have power p over here, okay. But you need not worry. When we solve, what we do is, so first you will find corresponding to p is equal to 2. First generalized eigenvector that you will obtain corresponds to p is equal to 2. Okay. So how do you go about it is a minus lambda I square v is equal to 0. This can be rewritten as a minus lambda I multiplied by a minus lambda I, v is equal to 0. Okay. If you look at this part, okay, and you, let's say, rename this as, let's say, x. Okay. What does this mean? A minus lambda I, x is equal to 0. This is the exact definition for your eigenvector, right? This means your x is an eigenvector. So what you want is, let's say v is an eigenvector, then a generalized eigenvector v2 is given by a minus lambda I, v2 is equal to v1. So earlier you used to solve if lambda I, v is equal to 0. Now you will solve a minus lambda I, v2 is equal to v1, where v1 is an eigenvector that you have already obtained. Okay. Let's use this. Okay. Okay. So what we want is, we want a minus lambda I, v2 is equal to v1. So now let's take any one of these eigenvectors, we will obtain a generalized eigenvector. Okay. So what is a minus lambda I? Lambda is 1. So this is 0, 1, 1, and rest of them is 0. So this is 0, 1, 1, 0, 0, 0, 0, 0, 0, v1, v2, v3. Is equal to a minus lambda I. Okay. So this again gives you, from the first row, it gives you a condition that v2 plus v3 is equal to 0, right? So this means v2 is equal to minus v3. Right? Just a second. Okay. So this is the condition that you just get from first of them. But if you look at the second and third row, right, what does this give you? Second and third row gives you that 0 is equal to 1, 0 is equal to minus 1, which is definitely not possible, right? So if we chose this particular eigenvector for solving this thing, then we got no solution. Okay, so let's try with the second one. Okay, now if you look at the second one, what we had is that my v1 variable is free and you should satisfy the condition v2 is equal to minus v3, right? But if you look at this a minus lambda times v2, what you are getting is your second and third entries are always 0. Okay, so we want an eigenvector for which your second and third entry is 0. Okay, and your v1 is free. v1 can take any value, but you should just satisfy this condition v2 and v3. So a linearly dependent on these two, but eigenvector can be 1, 0, 0, right? For this also v2 is equal to minus v3 and v1 is free, right? So what you get is from there, what you get is 0, 1, 1, 0, 0, 0, 0, 0, 0, v1, v2, v3 is equal to 1, 0, 0. This would imply v2 plus v3 is equal to 1, right? And again, your v1 is independent. Okay. Rest everything is 0 is equal to 0, right? So a generalized eigenvector is 0, half, half. This is a possibility, right? So now when you write S, your S, first you write your eigenvectors. Eigenvector is 0, 1, minus 1, 0, 1, minus 1. Then you have 1, 0, 0, and then you have your generalized eigenvector. Okay, so your A can be written as this. Then you write the Jordan canonical form. So your first vector, for the first vector, you don't have any generalized eigenvector, right? So you will have a Jordan block of size 1 cross 1. So this is 1, right? Then you have 1, 1, 1, 0, 0, 0, 0, 0. And then in the last, you have inverse of this particular matrix. Okay. So this is how you find Jordan decomposition or Jordan canonical decomposition of any arbitrary matrix. Okay. Let's solve one more example where we will find Jordan canonical form. Again, this is a upper triangular matrix. So its eigenvalues are given by minus 1, comma, minus 1, comma, minus 1, right? So let's first solve A minus lambda I V is equal to 0. This would become 0, minus 1, 0, 0, 0, minus 2, 0, 0, 0, right? V1, V2, V3 is equal to 0, right? So what does this give us? So if you calculate the first row, it gives you V1 is equal to 0. Sorry, it gives you V2 is equal to 0. Second row gives you V3 is equal to 0. And your V1 is free, right? So eigenvector is 1, 0, 0. Okay. Now, your geometric multiplicity and arithmetic multiplicity. Arithmetic multiplicity was 3. Geometric multiplicity is 1. So you will have one Jordan block of size 3. How would that look? Minus 1, minus 1, minus 1, 1, 1, 0, 0, 0, 0. Right? This is your Jordan block. This is your matrix J. Now, when you find out S, for your S, you should have 3 Li vectors, right? You should have 3 Li vectors, but you have only one Li vector with you right now. So we will solve for generalized eigenvector. So what we will do is, this is A minus lambda I. A minus lambda is 0, minus 1, 0, 0, 0, minus 2, 0, 0, 0. This multiplied by some V1, V2, V3 is equal to your eigenvector, which is 1, 0, 0, right? So what does this give us? So this gives you minus of V2 is equal to 1, or V2 is equal to minus 1, V3 is 0, and your V1 is independent. Okay. So let's take V1 as 0 only. It makes our life easier. So what would this give us? This would give us, let's say, mu2, that is equivalent to 0, minus 1, 0. Now in order to find the third generalized eigenvector, what we will do? We will do A minus lambda I mu2, sorry, this sum V is equal to mu2, right? And this again would be given by right. So from first row, we don't have any inference. Third row gives that minus 2 times V3 is minus 1, or V3 is half. So we have our third generalized eigenvector, that is 0, 0, half. Okay. So we can have our S as, this first one was 1, 0, 0, then 0, minus 1, 0, then 0, 0, half. Okay. So then you can write your A as S, J, S inverse. I hope this was clear. Okay. Now let's briefly talk about what is known as polar decomposition. Okay. So for a square matrix, your polar decomposition for a matrix A is given by W times P, where W is some orthogonal matrix, right? So what is an orthogonal matrix? Orthogonal matrix is a matrix which satisfies W transpose W is equal to W transpose is identity. Okay. And your P is some positive semi-definite matrix. Okay. Now, how can you calculate it? Let's say you calculated the singular valued decomposition of a matrix A, right? Then from here you can calculate your W as UV transpose, right? And you can calculate your P as V. So V sigma V transpose. Okay. So this is what I had in plan for today. If you have any doubt, you can please ask. Like, this is what I had planned for today.